right, so going through Recitation Guide 8, I'm going to do my normal thing where I just go through a couple of them. I notice that not a lot of people are watching these, so I'm just going to make this very simple and sweet. These are, as always, something to serve for you as an extra place to go where I go through the problems in a different way to what I do during recitation. So please check these out, even though no one's watching this video now, and I will always direct them to this now very fun introductory message of me telling you to look at this. Okay, so for number 1, you want to prepare a buffer solution with a pH range of 7 to 7.5. Which of the following mixtures would you choose? We now have to think, I'm looking at this equations and I'm like, okay, pH to Ka. How am I going to relate these? Well, I know pH equals pKa plus the log of the conjugate base over the conjugate acid. But, if we were to say that we took, say, the concentration of the conjugate conjugate base, in this case, the acid and the conjugate base and so forth for each of these, I could then say, okay, I don't need to care about this plus log part, where we have this plus log of those two things. And the reason for that is I don't have to worry about them because they're all going to be the same, right? So if I have that going forward, then I can say, all right, I can just ignore the second half, because if I ignore the second half, it makes this equation much easier. The pH just equals Ka, which is what we want. So with that in mind, I'm just going to say, okay, I'm not going to care about this. I'm just going to make them the same. And then I'm going to say, okay, I have the pH equals the pKa. I know the pKa is the negative log of Ka. So if I take the negative log of all these Ka values, I'm going to figure out what's going on and get a better, clearer picture of my pH. So that means I can automatically rule out C, right? It doesn't have a Ka value. So I'm not going to be able to choose that one. I have no idea what its buffering capacity is. Now, when I go through and I take the negative log of all of the rest of them, I'm going to see, okay, when I take the negative log of this Ka for A, I get 9.25, and that is quite high. That doesn't sit anywhere in between 7 and 7.5. When I take the negative log of 4.5, I get now 3.35, which again is very, very high, very, very low now. Now I've got a very low pH pKa relationship. And finally, when I do it for D, I get 7.02. There we go. That seems like something that's between 7 and 7.5. So I am definitely going to pick D as my winner. The thing that you want to do when you're working forward with these is just essentially looking at those Ka values and remembering you do have an equation that relates them. Just remembering, again, that the negative log of the Ka is going to also equal your pKa. Okay, I'm not going to do 2 or 3, so we're going to move forward. Write out the reaction between this and water, and remember that this is a weak acid. Okay, so with that being said, I'm just going to copy and paste. I'm going to say this plus H2O, and then say, okay, this is going to become my conjugate base, which I know very well, but I have my minus sign, and I take this down, plus, and then of course our wonderfully great hydronium ion. The reason we know all this and we can make these assumptions essentially is that whenever you see water, you must assume that what's going on here is going to be the hydronium ion going in there at the end. That's going to be always a product then if you have with water. So it's then just to say, well, this must be my hydrogen donor. It's going to give that hydrogen to this base, and it's going to lead to my conjugate base because it would accept the hydrogen going that way, and it's going to gain hydrogen. So this would be my acceptor, accepts hydrogen from him to get this now conjugate acid. So, in which direction would the equilibrium shift if you add NaOH to the situation? So, this is a weak acid, and when I think about a weak acid, I'm going to be now adding some NaOH on this side, right? So if I put NaOH here, I'm now adding OH minus, right? Because that we know that this essentially, it's a strong base, it breaks down completely. OH minus, when we look at this, is just another base. So it's going to just add on to the side as per usual, right? Because when I think about NaOH, I know that it's a strong base. I know strong bases, like strong acids, completely dissociate. I now have another ion on this side. I know moving forward, it's not going to change how many products I have on this side, right? We're still going to have this much water, so it's still going to shift to the right when I think about this, okay? So our reasoning is that we're adding in a base, but even though this is probably a weaker base than my OH minus, it's still just going to be making H3O plus, which means that it's not creating any extra product. So that's why we have this now coming here. So we're going to just, I still have my draw on. We're just going to say no extra products created, only adding a reactant, and therefore will equal a shift to the right because there are less ions on the, a shift to the right because there are less ions on the right. Okay, that's what we're looking for. Okay, moving on. Now I'm going to erase all this because we're going to move on to something different here. So what if you added HCl? So now I'm putting, my H plus, my Cl minus, which is going to come out over here now because we added NaOH and that OH minus was just not affecting this. But now I have my HCl and that's going to now, or my HCl, this is adding an H to this, right? Because now we've got H2O, H3O plus, and this H. So now there's got to be two of these and two of this. And when we would go through and balance this whole equation, we know that it would come out different. I'm saying you don't have to actually just balance the whole equation. You can just say, I'm adding now HCl to this problem. And if I add HCl, this is going to be a bigger issue because I'm now going to have to go through and work out, okay, I've got to now have, I have 1, 2, 3, 4 hydrogens. So this is now going to add an H3O plus plus another H to that H3O plus, but it's going to come out as a form of a hydrogen, which would not happen with my Na plus. It wouldn't add to the pH stuff in general. And again, we have our OH minus, which was similar to the other side. So that part stays the same. This Cl minus and this OH minus are essentially the same to us, right? But what really counts is we now have an H plus, which is going to add into my product. So what we're now going to see now is a shift to the left, right? Because now we've got this plus my Cl minus, which in comparison to before, where we say we had our NaOH, which then when we kind of say what became important, it was just my OH minus, right? Because that's what really essentially affects this side. So this would be a shift to the right, but this would be a shift to the left because now I've got 1, 2, 3, and here I've got 1, 2, 3, 4. So this now is going to shift to the left, and that is because shift to the left, we now have more products than reactants, and so we will see the reaction try to equilibrate by shifting to the side with less ions. All right. Great start. So now there are 3 hydrogens in this molecule. Will this make it polyprotic? If so, please write out why. Well, we can look at this and say with absolute certainty that it would not be polyprotic, right? Because once we lose that, we have this conjugate base, and that conjugate base has CH2, which we know is nonpolar. And since that is nonpolar, we know that it is definitely not polyprotic. Definitely not. Okay. We're going to skip 5 and 6, wherever my 7 went. Here's 8. Okay, so we're going to go through 8. Bronsted-Lowry acid. We need to remember Bronsted-Lowry acids are the ones that acids are the ones that proton donate. We kind of hinted at it before when we were talking about all the way up here. We were saying who is getting something and who is receiving something. These are why these definitions are so important. They help you make sense of which side things will shift to. And so, of course, we mean that the Bronsted-Lowry base is the one who accepts that hydrogen happily, right? And then we know a Lewis acid, we're talking about those that are the protons, have the protons in general. So those are the ones that we look at and say, okay, those are the E-pair acceptors in that sense. So they will take an E-pair because they are not as electron negative. So they will accept, and I'm just going to put ACCEPT to keep that short. And then these ones are going to E-pair donate, because again, we think of bases as being something that has more electrons and therefore can give away electrons. So, you know, things like OH minus, Cl minus, those minus signs are actually those E pairs, right? So that's the E pair. This plus sign will want a negative sign. So it will accept this negative to this positive to make it neutral. All right, and finally, circle the buffering region in the following chart. Well, I'm going to highlight it instead. This right here, guys, is the buffer region. So it then says, estimate the pKa of a weak acid. Well, the wonderful thing about weak acids, and the same can be said for weak bases, because in the weak bases, the same thing occurs, it's just that it equals the pKb and not the pKa, right? Because base, acid, bases, Kb, acids, Ka. But what we see here is with the equivalence point, if I go over here, we're just going to estimate and say that this is at 8.5, okay? Now, the fun thing about this is we can then say that there's a half equivalence point that we can say will be here. And the reason why is it's literally 1/2 of this. So 8.5 divided by 2 would be 4.25. And that's going to be my half equivalence point. Now, you know what's so cool about this is that we look over here and that's measuring pH, and that's never going to change. So this is the pH. But also at the half equivalence point for a weak acid, that also equals the pKa. And so in that, you do not have to worry about trying to figure it out using the Henderson-Hasselbalch equation. You can literally just go from the equivalence point, divide it in half, and then you'll find it. The reason why we show you this here is because the biggest thing I would do is take out a ruler, put it up to there, see what that number is, because as you can see, this is where I would assume 9 is on the pH scale. So this is between 9 and 8. And you really want to make sure you get that right, because then when you're estimating your half equivalence point, it's literally just dividing that in 2. And if you don't start off with the right numbers, you won't end with the right numbers, right? So we want to make sure that you start and end correctly. So be sure you do that when you find your equivalence point, because if you find an incorrect equivalence point, your half equivalence point will be incorrect, which means the pH and the pKa will be incorrect, okay? So just putting that out there. All right, guys, thank you so much for watching, and I will see you guys next week.